Welcome to the 30-minute presentation about our paper titled Full Abstract from Static to Gradual. My name is Koen, and this was in collaboration with Amin and Dominique. So, what's in this presentation? Well, first of all, we're going to give you a bit of a background in gradual typing. Then we're going to introduce our criterion that the embedding from the static language into the gradual one should be fully abstract. We're going to explain this in detail, after which we'll show that it is indeed useful and realistic. And finally, we'll finish off with some conclusions. Okay, so first things first. What is a gradual language? Well, in a gradual language, we want to combine static code with dynamic code. Right, both have their pros and cons. In static language, we've got static guarantees, but our development might be a bit more slow and less flexible. In a dynamic language, you have lots of runtime errors, but our development can be a bit more fast and more flexible. So in a gradual language, we want both these languages to embed it into it. But what's more, we want to have this continuous spectrum between the two. In some parts of the codebase, we might want to go more to the static side, and in other parts of the codebase, we might want to go more to the dynamic side. So what should a good gradual language look like? Well, there's lots of things to this question, but one of them should be that, okay, if you have a gradual codebase and you have some portion of it which is fully statically typed, then locally in that statically typed portion of your gradual codebase, you want, of course, to enjoy the benefits of static types. Of course, this raises the question, what are these benefits exactly? So at least one of them should be type safety. In the static language, you've got type safety, while in a dynamic language, you just got runtime errors. So in a gradual language, you want to enjoy the benefits of type safety in a statically typed portion. So you can phrase this as the statically typed portions of your code are never to blame for a runtime error. So if this gradual program gives you a runtime error, the statically typed portion is not to blame. This is an application of the blame theorem, and it has also been proposed as a generic criterion for a sensible gradual language. So this is one of these refined criteria by Jeremy Siek. Of course, there's much more to static types than just type safety. In a terminating language, for instance, if you have an expression of type bool, we might care that it actually always will evaluate to either true or false. In a polymorphic language, we might care about some notion of parametricity, which is satisfied such that if we have a function for all x to that, for instance, such a function modulo divergence will always act as a constant function. In an information flow language, we might care about some notion of non-interference that is satisfied, such that if we have a function that takes a high confidentiality boolean and maps it into a low confidentiality boolean, then that such a function can never really depend upon its input argument. And so Ronald and Eric already make this point that, okay, if you have a static language and you want to gradualize it, you should be very careful to explicitly denote the intended meaning of the static types that you want to preserve upon your gradualization. Right now, though, we want to take a bit of a different perspective. And this will lead us to the fully abstract embedding criterion. So, given the question, what's to be preserved upon gradualization? Well, earlier we said, okay, in the statically typed portions, we want to enjoy the benefits of static types, including, for instance, some notion of parametricity, correctness, or non-interference. Then the question becomes, okay, does everything that a static language programmer cares about or relies upon when reasoning about static code, does that follow from these notions? Well, in general, this might not be the case, right? In general, it's almost certainly not the case. A static language programmer can care about something which is not implied by your notion of parametricity or correctness. So what we want to do is look at things a bit more optimistically now. So given this set of all static reasoning principles, we are going to try to encompass that a bit more broadly, and then we're going to try to preserve that. And this is exactly what we'll try to enforce with the fully abstract embedding criterion. So, okay, what is full abstraction? Well, to explain this, we're going to need the notion of contextual equivalence. So two terms are equivalent if we can always interchange the two, no matter what the surrounding code might be. So formally, E is equivalent to E prime, if and only if, for every context C, so that's a program with a hole in it, you can plug in either E or E prime, we'll obtain two programs that behave the same. And then what we want to do is we will want to enforce that this contextual equivalence is preserved. So if E and E prime are equivalent, then so must be their embeddings. So practically this means that given a gradual code base with some static code in it, we can just freely use the refactorings that we know from the static language. So this has already been proposed by the paper called Parametricity versus the Universal Type. In our paper here, we investigated a bit more thoroughly. So okay, the embedding from the static language into the gradual one is fully abstract, even only if contextual equivalence is preserved, and reversely, it must also be reflected. So this is the reverse direction. So if the embeddings are equivalent, then so must be the original terms. This is a bit less interesting because it follows from the fact that the static language is contained in the gradual one. So indeed, given the fact that no gradual context can distinguish between two terms, we must prove that no static context can either. But a static context is just a special case of a gradual context. So this indeed follows naturally from the fact that the static language is contained in the gradual one. And this is exactly one of the refined criteria. But is it actually useful? Well, we argue that it is by looking at some counterexamples. So for the first two counterexamples, we're going to look at examples where failure of FAE will show that the gradualizations are faulty. So for the first example, we're going to look at this paper. So in this paper, they gradualize a polymorphic language. But before they do that, they just quickly showcase that, okay, if you naively apply the framework from this other paper, you get a naive gradualization. That although it satisfies all refined criteria, it does not satisfy parametricity. So they have this explicit example of this function for all x to z, which will basically act as a successor function when you apply it to z. But we can show now that the same naivety is also exposed by failure of FAE. So indeed, we can consider this equivalence in static language. So we take a function for all x to z, instantiate it with z, and in the first term, we apply to it 0. In the second term, we apply to it 5. In the embedding, however, the same equivalence does not hold anymore. Indeed, we can apply it with this f. So in the first one, it will evaluate to 1. In the second one, it will evaluate to 6. So for the second example, we're going to look at this paper. So in this paper, they gradualize an information flow language. But before they do that, they also showcase that, okay, if you naively apply abstract gradual typing, you get a gradualization that, although it satisfies all the refined criteria, it does not satisfy non-interference. Indeed, they give this example where they can type this function from a high confidentiality boolean to a low one, which will basically strip the confidentiality of the input boolean. So indeed, they can apply this function with true typed a high confidentiality boolean, and then it will evaluate to true low. We see now that the same naivety can be exposed by failure of FAE. Indeed, you can consider this equivalence in the static language. So we take a function from BH to below, we take a boolean BH, and here we apply f with B. In the second term, we apply f with the negation of B. In the embedding, however, this is not equivalent anymore. Indeed, because the first one, if you apply it with f and b, in the first one, this will evaluate to true low. In the second one, this will evaluate to false low. For the third example, we're going to see a gradualization for which failure of FAE will provide like an interesting perspective. So for the static language, we're going to look at total STLC, in which we have the following equivalence. So we take a function from bool to bool. In the first one, we're going to take the second projection out of a pair in which this second component is 43. In the first component, we have f applied with true, but f applied with true to always terminate. So indeed, this will always evaluate to f to 43 upon application. And so it's equivalent to this function, which will just unconditionally return 43. In the embedding, however, if you look at the gradually typed lambda-calculus, the same equivalence does not hold anymore. Indeed, you can now type a function from bool to bool, which will always diverge upon application, or a function that will always return a cast error upon application. And so we see that indeed this equivalence is broken here. So we can then wonder, okay, is the GTLC maybe more naturally viewed as a gradualization of a partial variant of STLC? So for the fourth example, we're going to look at an example from this paper. So we start with a recursive system F as our static language, and then we can make the observation that this type here, there exists a Y, such that for every type you can embed into it and project out of it again, that such a type doesn't have any interesting inhabitants. In other words, every inhabitant must be uninteresting. So this follows from the parametricity, Reynolds parametricity that you have in this language. So what does it mean for a value to be uninteresting? So let's define this a bit. So suppose that you have a value f, and so suppose you have the unpacking, we call it u. Suppose that you instantiate it with a boolean, for instance. So you now have an injection from boolean to this y type and the projection. So you can pattern match this with an I and a p, and suppose that we then actually use this pair. So if you actually inject through and project out of it again, well, parametricity says that this will necessarily diverge. So that FF is in a certain sense not really interesting. But we can actually use this observation to construct a interesting equivalence. So E1 is equivalent to E2, where E1 we define as follows. So in both terms, we take a function f, we take a value f from this very big type. In the first one, we go through all these steps and then actually use this injection and projection pair on true. So we already saw that this has to diverge because of parametricity here. In the second one, we also take this function of this very big type, but we just unconditionally diverge upon application. So indeed, E1 is equivalent to E2. But then we can wonder, okay, is the same still true if you look at a gradualization of recursive system F? So are the embeddings still equivalent in the gradual language? Well, this is typically not the case, right? You can have this function, this gradual value of this type, where we actually instantiate this existential type with the unknown type, right? So we have the unpacked value as follows. So for instance, if you instantiate it with boolean, we have this pair of boolean to unknown and unknown to boolean, right? And here we instantiate this value by upcasting to the unknown and downcasting. So if we actually use this injection and projection pair on true, we have an upcast to unknown and a downcast again. So this will actually go to true. So if you remember, this equivalence does not hold anymore because in E1, this will actually evaluate to true if you apply it with this f. In E2, we just unconditionally diverge upon application. So this equivalence does not hold anymore. So even as we saw, if you're very careful about saying that you want to preserve parametricity upon gradualization, then the question still remains, okay, what kind of parametricity do you actually define in your gradual language? It's clear at least that defining some notion of parametricity is not, that the notion that you define in the gradual language is not always the same as the one in the static language, right? So for instance, if you look at the latest gradualization, something like system F, which is a very nice proposal from last year at POPL. It's a language that satisfies all the refined criteria and also satisfies parametricity, but the parametricity that they prove here for the gradual language is not the same as the one from the static language, right? In the static language, we have Reynolds one, in which values of this type cannot be interesting. In the gradual language, however, we saw that it can have an interesting value. So to sum up, we can wonder, okay, is it possible to gradualize something like recursive system F such that we just preserve any static equivalence, and hence the parametricity in the gradual language will be more alike to the parametricity in the static one? You might wonder now though, is it actually realistic as a generic criterion for gradual languages? Well, we argue that it is, because we've proven it for the embedding from the simply typed lambda-calculus with recursive types into its gradualization. And we've also proven this in Calc. So what we want to do now is to give you a bit of intuition on how we've proven this. But to do so, we are first going to give the briefest introduction about the GTLC. So let's talk a little bit about the type checking first. So for the types, you can first start from the grammar of the static types. So we've got our base types, or arrow types, product, sum, type variables, and recursive types. In the gradual language, we just add one entity to this, which is the unknown type. You can then look at a static typing rule for function application, for instance. So if we have an e from tau 1 to tau 2 and an e prime from tau 1 prime, then we have that e applied with e prime is of tau 2 even only if tau 1 is really equal to tau 1 prime. In the gradual language, we want to relax this equality a bit and replace it by a consistency relation. And this consistency relation, very briefly, you can think of it as identity, but the question mark can serve as a wildcard. So let's look at some examples of this typing rule. Well, we can apply 6 with a identity function typed at the unknown, because indeed unknown is consistent with z. We can extend this example a bit, right? You can apply this thing at type unknown to an identity function of type z. Indeed, z is also consistent with unknown. We can expand it in a bit of a different way. So we can have this thing at type unknown and apply it to the identity function at type boolean, because indeed boolean is consistent with unknown. As a counterexample, we can apply 6 to the identity function typed at boolean, but of course 6 is not consistent, boolean is not consistent with z, and so this doesn't type check. So the job of type checking in the gradual language is not to exclude everything which is up to no good, but just to exclude everything for which you can statically derive that it is up to no good. So indeed, this one, we'll see that this will actually evaluate to 6 in the end, but this one should not evaluate to a boolean, right? We're going to try to use 6 as a boolean, which is of course not sensible. So let's look at the dynamics then. So the dynamics are actually defined by a translation into a cost calculus. And this cost calculus, it's basically just the same as GTLCmU, but we add 2 extra constructs to it. So we're adding cost errors, and we're adding an explicit cost construct from an initial type to a final type. And this cost error here is just a stuck term. So let's look at some examples, right? If we had this term, if we want to translate that into the cost calculus, well, we're doing that by everywhere where we used consistency in the typing derivation, we're going to insert an explicit cost. Here 6, where we were using that as something of the type unknown, so we're inserting an explicit cost from z to unknown here. Here we're using unknown as something of type z, so we're inserting this explicit cost unknown to z here. This will evaluate to 6 from z to unknown to z, and then we have another evaluation rule that this will go to 6. Another example, we have this, which we now translate to the cost calculus. So here we have the same cost that we insert. Here we have the cost from unknown to Boolean. Then we have the same evaluation rules, which will have this be evaluated to 6 from that to unknown to Boolean. And then we have also an evaluation rule that this will go to a cost error, of course. So okay, let's give you now a bit of an idea on how we've proven this. So remember what we need to prove, right? So we need to prove that equivalence is preserved. So given these two terms which are preserved, we need to prove that the embeddings are also equivalent. So what you need to prove is that, okay, if no static context can distinguish between these two static terms, then no gradual context can either. So what we want to do is we want to try to emulate the behavior of a gradual context by that of a static one. So how are we going to do this? Well, we're going to backtranslate terms of the unknown type to this very big static type. So we've got a recursive type here, and then we've got a sum over all these different types. So we've got all our base types here, and we've got also different branches for all the other typing constructs. So every static type we can embed into this type, and we can project out of it again. And so this idea of this kind of like universal type is similar to this, to what they do in these other papers. So what we want to do now is, well, the behavior of this gradual context is actually defined in terms of this cost calculus. So we want to backtranslate, we want to emulate or backtranslate this whole costing business. So if you have this explicit cost from E from initial type tau to a type tau prime, we're going to backtranslate that to a function applied to the backtranslation of E. And that function will be a function of the backtranslation of tau to the backtranslation of tau prime. So let's just look at some very simple examples of this. So if we have 6, if you cost it up from that to the unknown, we're going to backtranslate this to a function that we'll call inject z applied to 6. So inject z will take an integer, and basically it will inject it into the right branch of this recursive type. If we then have another example, if we have some E that we downcast from the unknown to z, well, we will backtranslate E itself and then apply it to the function called extract z. Extract z will take something of this unknown type, of this universal type, and give us back an integer. How will it do it? Well, it will check if it is of the right form, right? If it is of the right form, then it will just return the integer. If it is of a wrong form, then it will just diverge, right? It will avoid giving us back an integer. As another example, we have exactly the same when we downcast something from the unknown to a Boolean. So you can look at some examples, right? We saw earlier these examples of this example of z from z to unknown to z again, which will just evaluate to 6. In the back translation, we first inject 6 into this universe such that it will be of this form, and then we just extract it out of it again, which will eventually also evaluate to 6. As another example, we had this 6 from z to unknown to Boolean, which of course is not sensible, so we don't want to return a value here. So here we give the stuck term, here we evaluated the stuck term cost error. In the back translation here, we inject 6 into the universe and then we try to extract it. But remember, if it was not of the right form, which is the case here because it's now an integer, then it will diverge here. So indeed, we're also not returning any value of a Boolean here. We're also using two logical relations, both modeling some kind of refinement. We use them primarily to prove the correctness of our back translation, and both relations, they relate static terms with their embeddings and gradual terms with our back translation. Because of step indexing, we define them in Aarhus, which makes it more easy to reason about and model the recursive types and the unknown type. So lastly, we're finishing with some conclusions now. So first, as a quick recap, instead of trying to preserve a chosen meaning of types upon gradualization for the statically typed portions, we want to try to preserve static reasoning principles more maximally. And this is exactly what FAE will do with respect to contextual equivalence, right? So we want to preserve arbitrary static equivalence upon gradualization. We saw that FAE is useful. Indeed, failure of it can expose gradualizations that are clearly faulty. We had the one that broke non-interference and the one that broke parametricity. We also saw that failure of FAE can offer some interesting perspectives about existing gradualizations. So we saw indeed that GTLC might be more amenable as a gradualization of a partial STLC as opposed to total STLC. And we also saw that state-of-the-art like parametric gradualizations do indeed nevertheless lose some static reasoning. We also saw that FAE is realistic. Indeed, you have proven it for the simply typed lambda-calculus with recursive types into its gradualization. Lastly, we want to say that, okay, ideally FAE is satisfied for a particular gradualization. If not, however, yeah, we want to say that, okay, it's good to know about it, right? Because some static reasoning principles are not preserved. We also want to say that, okay, further investigation here is definitely interesting. You can ask yourself, okay, is it recoverable? Is it unavoidable? And if so, why? You can ask yourself, okay, which equivalences are exactly broken or which one are preserved? How are they broken? And then also you can check if your gradualization might be a bit more natural with respect to another static language, like we did with GTLC. Thank you all for watching. This concludes our presentation.